Morning, everyone. Welcome back. Welcome back to SOC100. Good to see everybody. Good morning, good afternoon, good evening if you're over across the pond. Good to have everyone back in the room, back for another episode of SOC100. Another stream, Windows Triage today. Diving deeper into processes and threads and all that good stuff. So let's take a look. Looks like we've got some people still rolling in right now, but a decent sized morning crew already. How's everyone doing? Raj, what's going on? Welcome. Quad 9. Nice. Alan, good to see you. Bearded, Tom, Kim, Karina. Who else we got inside the chat over here? 89, Cap City. Cap, it's good to see you back as well, too. Haven't seen you in a little bit. Finac, Patricia, KS, of course. First to the chat, KS as well. Oh, you got your new chair? The steel case Leap? Was that the one, right? Oh yeah. Yeah, it's the same one right here that I'm on. So good. Like literally no leg or lower back fatigue ever. And I've sat in this chair for like easily some 12 to 14 hour sessions, maybe a little bit longer. Obviously with like breaks getting up stuff, but I've had some real long days in this chair and literally no leg or lower back fatigue. So good choice. Bearded, your brain is fried from all the information at work. Yeah, this is the big week. So what's it like? What's it like being in the SOC finally, huh? What's it like looking at the glass, all the tickets, the alerts, the incidents? You should share a little story if you can. Yeah? Beard, are you actually making a YouTube video? That's pretty cool. Have to check that out. Well, Bearded, you're making a YouTube video now. Just so you know, man. You're not getting away from that. Chat has declared. Cool. So we have a good stream today. So we're going to be diving back into Windows Triage today. Well, learning and getting there. I think we'll have enough time to get to the first start of the security analyst skill set with your tools. We'll see. We do have a lot to cover. We've got several labs that we're going to go over today and some lectures just to make sure that we're all tracking on all those key points, but we'll see if we can get to the actual Sysinternals portion by the end of it and start sifting through some homebrew malware that we prepared for you. Bearded saying, seriously though, I understand when people say when you do what you love, it doesn't feel like work. It just feels like I'm in a bigger and never-ending environment of learning on a bigger scale with people that love the process as well. Yeah, man. It's a really good feeling when you've worked hard for something, you've specialized in it, you've developed your trade, your craft, and then you're able to do that and provide value and then be rewarded with, like, you know, obviously you're getting paid, right? Like, and you're getting praised and recognized, and then you're working with others in the same boat. It's a really good feeling. So I'm glad you're actually getting to enjoy that side of things now. Cool. Nice. Okay, we're up to 30 now. A couple more people rolling in. We'll give another minute or so. We're going to dive into some stuff. The hard part is juggling all the responsibility with school. Yeah, family studies, etc. after work. Yeah, so you know, I think I feel like I was talking about that like a week or two ago. Like once you're in the field, like the hardest part is getting in, working your way inside of it, the study, the grind. But then when you're actually in the field, you're going to notice like you're actually going to stop. You're not going to be studying that much. Like you're going to kind of come down a little bit. It's not feasible, right? Because like your day job, especially inside of security, is so dynamic. You're always going to be having an essence of learning. It doesn't matter how skilled or how advanced you are. There is learning to do like every day, every week. So eventually you're probably going to start scaling down from like cert hunting and course hunting, and you if you're like me, like that's why my Security Plus expired years back, and I was like, well, that's that. Same with Dan the other day inside Discord, like his as well too. It's gonna happen, and that's just the hardest part. The biggest grind is getting into it, and then you're gonna find a better balance. So give it some time, man. You're probably gonna start getting out of like study grind mode slowly, like over the next like weeks and months, and then you're just gonna have like a little bit of study grind per week, and then your day job's gonna keep you pretty busy. It's a good thing. It's a sign of growth. Ariel, good morning. Good to have you back. CI to you as well. Good to have you back with us. Cool. All right. Let's jump into it. Hope everyone's got their coffees ready and stuff. Yeah. Yeah, Beard, you know, like it's the same thing. Like you'll notice that like if you talk to a lot of professionals in the field that have been doing this for a couple of years, like CTFs, right? Like they don't really get too involved with them anymore. Maybe like once in a while. It's sign of growing up. All right. KS Anthony flexing with the fancy cups. Yeah, today's a red mug day. I felt like I needed some vibrancy. KS Day 57 asking for black level effect mug. I need to get like a soon trademark emoji. I think that's what I need. It's coming. We're gonna get all the emojis, all the swag, everything you guys all have been asking for. Demorier, sorry to hear. Yeah, you're having a bit of a rough week over there. It's kind of crappy. Hard drive dying. It's the worst. And the NAS. Well, good to have you with us, though. Hopefully today will be a nice reprieve from all of that, and you can kind of zone out a little bit, chill out with us a little bit, and kind of take a break from life for a little bit. I hope things start to get better from you soon. Tom, you know, look your set when you see it. Yeah. Yeah, them fancy mugs. All right. It's enough jib jabber. Let's start diving into some things. Okay. So today we are on, today's January 18th, Windows Triage, malware analysis. So we're going to dive back into that. Last week, we just kicked off this module, and we started working with a breakdown of processes, threads, and virtual memory, kind of understand those things, and we did a little bit of a walkthrough with Process Explorer, or ProcExp. So kind of going back to our notes, where did we leave off? Yeah, so last week we were talking a little bit about like the stack and the heap. It's kind of like where we left off with things, virtual memory allocation, and I think we're going to be able to dive back in a little bit more of that today. Now, we're not going to go super deep into this stuff because, I mean, truthfully, SOC Tier 1 analysts are not performing reverse engineering tasks or analyzing the stack and heap of a binary. It'd be great like if you were at that level for that level, but it's quite advanced. So that's why we're going to talk a little bit more about it, maybe just kind of at a cursory level, so we get it. But we want you to be triaging those perimeter security alerts, users downloading, clicking on things, you know, like an auto run appearing after startup, things like that. Like that's what we want you to get familiar with first. So that's where we left off. And today is class 23. Cool. Y'all ready? Everyone ready? Y'all ready for this? Cool. Cool. All right. Ready check, yeah? Can I do that? I wonder if Twitch, if I can like force like a ready check on everyone. I need to find out how to do that. That'd be actually really handy. Like a little pop-up. Look into that later. Okay. Okay, so let's dive back into things. So class 23, we were last off with the stack and the heap. So a little bit of I guess like a bit of a segue. Well, let's talk about that a little bit more, and then we're going to dive into things. So the stack, right? There's a reason why it's called the stack, okay? And there's a reason why we have this concept of the heap and these two types of memory structures. So I'm going to kind of like visually draw some stuff over here, so we can get an idea of what these memory things sort of look like at like a high level. Now, the stack we were mentioning is effectively the code. Like those are the instructions, and it works on this structure of LIFO. Last in, first out. Okay. So that is to say that when we have code of something like, you know, let x equal 2, something like this, or rather I should say, what I should say is var x equals 2. So if we have something like this, if we have these statements of code, what's happening here is inside of the stack memory, they go in and then they go out. And it's a stack for a reason. Truly. That's why we call it stack memory, because it just stacks up with calls and then they come out the same way. Like that's why it's last in, first out. So you can imagine like sets of instructions appear and they go. That's how code is actually being interpreted and executed inside of a process. So you write some code, you compile it, it turns into a binary, it turns into an executable, and then those instructions in the stack side of the memory is very performant, as we talked about. It's essentially automatic. Memory is assigned quite automatically for it and quite structured and controlled. There's memory protection for these types of things, so that certain memory is allocated for certain things, can't be interfered with, some is executable, some is not executable, etc. Again, we're not going to get too advanced in those areas, but just understand that there is memory protection that happens in these cases. Now, the heap and the other side of things is more of that dynamic type of memory. And as you can see, it visually, as a concept, will look quite different if you think about it. So the stack is like local variables, as we looked at variables in the past. And the heap would be more like global. Now, at a given time, if a thread is working, we talked about threads inside of the process, right? Process, you can imagine, is like this giant bucket, and we have a bunch of threads inside. Now, a thread in itself can be working with a stack of instructions. You know, if this equals to that, then do this. If this is greater than something, then do something. Loops, all those things that we kind of talked about before. We did a little bit of scripting earlier on, right? Now, what happens is when a thread is working with a stack of instructions, and let's just say that there is another function or there's another set of code happening inside of that stack. Well, it's actually going to branch out from here and open up another stack. You can only work with one at a time. And this is actually why when you have code and you have certain functions, and let me actually see if I can just pull something up on the screen, it'd probably be a little bit easier. If function passing variables. Maybe someone's got a script ready for me that I can take a look at over here. Right. So as you see, like we talked before about these arguments or these parameters, right, that we can put inside of a function call. And we're passing information back and forth. We looked at this in the past at a high level. This is why code is structured the way that it is. You can only be working with a stack of instructions at a given time, and that's the local scope. So if you're in a certain function, and this is important to start to pay attention to right here, because this is how vulnerabilities actually start to compromise the workstation, is you start messing around with this stack, like the way it's structured, the way it's pointing to different functions, different calls. You can only have one of these at a given time, and it steps through it. So if I pass a value to another function within a function, so if I say like if g is equal to 1, the if will start, like the statement begins. But once I get inside the brackets, or once I start getting to passing these arguments or these parameters, you're going to have a separate stack that has to effectively break that down and interpret what's going on inside. Once it does, it returns back to the original stack, which completes, and then off it goes. This is quite different than when we're dealing with things like from the heap. The heap memory is more global oriented. So the stack at any point could be referring to global instructions within inside of it, but it still has to execute the steps the same way. So why is this a problem? If after I've said everything that I've said right now, and I'll kind of recap it again, because I'm going to ask a question in the chat. If you're in this like conveyor belt of instructions where steps have to happen in a certain order and they're expected to happen, and then somewhere within that stack is a step to refer to something outside of it and then pull it back in and out. Why do you think that that's a bit of an issue? Like structurally speaking. Latency, yes. Yeah, that's right. We talked a little bit about race conditions. If it's something it can't control, yeah. Yep. Exactly, right? So like if there's a reference to something global, the local scope of the function has to continue executing that it's whatever it's designed to do. That's the code. Like the programmer has developed their code. It compiles, it executes through this stack of instructions. That whole LIFO structure, last in, first out, and that reference, right? Data cannot get corrupted. Well, it can. That's the problem. So if the program is just expecting to work with some type of global memory or some type of global scope, and the process is compromised, and that reference to a global variable is then altered or changed to increase the allotted memory for it, the program is just going to work with it if it's executed well. If the attacker is able to sort of pull this off and they pull off a special, very crafted attack. Again, we're not going to get too advanced because we're still in like this tier 1 level. But the concept being is if more memory is brought back into the process of instructions kind of happening, right? it's just going to execute it. And this is where we get into weird vulnerabilities where like another shell command, another scripting command, another system execution can occur within inside of a stack of instructions. And it's just going to execute because it's trusted. So Tom's saying if we can't find the reference stack and get messed up, it can. Yeah, this is where you get like systems that crash. This is where like running certain malware, or if you get infected with a certain virus on your workstation, things just like crash, like they just hang up because it's a good effort, right? Like the threat actor has compiled something that works most of the time, but maybe not every time, or maybe they didn't account for certain protection inside the memory, or certain protection from like an EDR tool on the endpoint itself. But it's important to understand that this structure exists for a reason. The stack memory is extremely performant, right? It has to work that way so that it's fast, it's reliable, it's predictable, and it can be contained. The heap memory, on the other hand, can get out of control. This is why you hear a lot of programmers are always mentioning, like, try to keep the scope local. This is why, like, when you're reading those Python tutorials that some of you have started, or you've started programming scripting, there's a huge emphasis on trying to get away from global scope and trying to work with local scope. So for those of you that are starting to get interested more in AppSec, application security, this is why you're looking for those types of vulnerabilities in the first place and trying to make your code more performant, more optimal, more clean, more protected from potential vulnerabilities. So understanding these structures is important because it starts to open up the path to understanding vulnerabilities in general that could be impacting code or memory execution. So see, I was saying, would that be like virtual memory? It could be both. So the stack and the heap could be referring to physical and virtual memory at the same time. It's really going to be depending on what's running, how the program was compiled, the operating system itself. It has different preferences. Just understand that you're going to have physical memory effectively allocated first for the stack if possible, like that'd be preferable, and then some expansion into virtual memory. Whereas, and the heap, similar, but you can get away with a little bit more virtual memory in that case, because again, it's a global scope, like you're going to be referring to things every now and then, ideally, as opposed to a local set of instructions. Yeah. Yes, yeah, so yeah, memory you're referencing, exactly. So again, if the stack is performing a set of instructions and it's expected to do certain things, and then there's a reference to something global, there's an assumption of trust. That's the problem, right? And so this kind of goes back to the concept we were talking many times about, the integrity component, right? Do we trust what is actually going on? And this is why we were trying to talk about last week that as a process is created, as we're going to dive into now, there are a series of steps that occur, right? And remember we said we have like ingredients that happen over here. Sure, I'm going to go with that. It's like kind of putting together, like you're cooking, you're baking, you're putting together like an apple pie, right? Or you're cooking something on the stove. These steps over here all have little checks and conditions to see, should I trust this? Now, when the process is running, after all those checks have happened, right, we have this stack memory that is calling things and taking things out, and it's just executing with a lot of assumed trust that has happened there in the first place. And this is why, if we can compromise something in global memory scope, it is easier to sort of get inside here and change one of those reference calls to something that is actually bad. Some malware over there. And this is why attackers, as we said last week, are interested in the runtime state of a process. Or rather, I should say a binary. A runtime state of the binary, because at this point, so much has happened beforehand that they could slip in easier, a little bit undetected. This is why you hear like fileless, in memory. You hear attacks happening that don't touch the disk because there's so many layers of protection that happen there, from writing the code to compiling it to executing it to checks to integrity checks along the way, etc. But once it's running, the runtime environment is a little bit less secure. And I see a couple things inside there in chat. So I'll say, oh, no, there's no questions. Wait, Finax got a question. Yeah, I'll get to you in a second. So imagine, right, like we had that castle, and this is kind of going back to the kernel now. And there's sort of this perimeter of events. Well, the castle is going to be the most secure. But it gets less and less secure the further you get away from it. And this is what's happening when a process is executed. Finax saying, so if we reference something outside the control of the program, you can effectively execute arbitrary code. Yes. This is how DLL injection happens. This is how process injection happens. This is how search order dependency attacks happen when Windows is looking for certain DLLs to load. When we're going to talk about the portable executables really soon. This is how the vulnerabilities occur, and this is why, because we have these two forms of memory that are executing instructions from a process, and they're expected to behave a certain way. But it's the late stage of the process being executed where the stack is already now firing off instructions where the attacker wants to get in. Again, this is where buffer overflows happen. Like I said, process injection, DLL injection, search order hijacking, you name it, fileless, in memory. All this stuff happens later on. The threat actor, if they can get to the source code, there's going to be a lot of steps along the way to prevent that malicious code to even fire off. Now, it's not that it's not going to happen, it's just a lot less likely to happen. So understanding how these two structures work and why they exist the way that they do should help prime you a little bit for what's coming ahead. This is why, again, we also say we don't want to like throw you, like you shouldn't be doing digital forensics at such a deep level at this point. Because if you're that tier 1 analyst, your job is out here. Okay? You're that SOC tier 1 analyst on that perimeter level of security, looking for anomalous activity happening with the runtime state of things. As you progress and tier up, this is why we had recommended you should start maybe focusing and studying a little bit more on deeper Windows internals, getting more advanced into defer and detection engineering and such. You don't need to worry about that yet. First things first is get an understanding of how these two structures work in memory, how the process executes, and where the vulnerabilities can occur as a result, and then learn some triage tools, which we're going to go through in this module, to start inspecting this kind of like this reflective activity of events that happen later on. Cool? That's what we're going to be covering. This is the Windows Triage module. This is what's getting you ready for Tier 1 analysis. Does that make sense? Kind of like walking through all that? Anyone unclear? Also, morning, Doug. Yes, that's why you can't battle the Elite Four in Pokemon without a good team first. That's right, man. That is why. That's why. Cool. Okay. So now that we've gotten a bit of an idea about that, let's actually let's work through like this, like the birth of the process in and of itself. Doug is saying, a question, which windows are we looking at, and is it going to be a pain? Nice. Doug, I appreciate the humor. Crazy, interesting. Honestly, it's wild and amazing. Yeah, man. Excuse me. That's right, our double. Karina, would you be able to recap that? Yeah, okay, so let's think about from like a recap perspective. Or wait, I think you've... Yeah, okay, so your question. In your diagram, it sounds like it's easier to inject into the stack. Correct. This is why we're saying the threat actors are looking for attacks and vulnerabilities in the runtime state of things, because looking at these two memory structures, right? We have our stack and our heap. The stack is a set of instructions that is effectively the step-by-step execution of your code. Like, variable x is equal to 2. If x is greater than 5, do something, etc. Like that, your code that you write, right? Now, there's a lot of things that have to happen for the program to get into a process runtime state, which, when it executes, puts your program instructions into a stack, which is a set of instructions. You think the program instructions aren't in the stack, just the local variables? Yeah, correct. Yeah, so we have the local variables that go inside of the stack itself. That's what's being referenced, like in a function. So like if x is equal to 2, if x is greater than 5, do this, do that, end program, end loop, etc. Like that's your stack of instructions that are happening a certain time per thread. And then if there's a function within a function, then what's going to happen is another stack is created, and then that is executed, and then it goes back to the original stack. Now we have our heap memory that's allocated for anything global within the program itself or other programs. And that's sort of the problem, is if you have functions that are dealing with local scope, but then have to creep out and deal with global references, which could be like allocating more memory if needed, pulling memory from the global state of the program itself. At that point in time, that global memory could be susceptible to things where we're trying to load maybe like a DLL, maybe start another thread, pull more process state information into the process. That's a bit of a problem, because inside there, when we start referencing things inside, bringing like that heap global scope into the local scope of the stack, it's more trusted at that state. And that's what I was trying to convey over there. That's kind of what Karina was I think, coming to the conclusion to, is the process to get to the stack set of instructions executing. You have the developer who wrote it. You have the code inside of your editor. You have your unit tests. You have your AppSec tool of choice plus team kind of scoping and creeping through your code, etc. There are so many steps just at that level. And then the process creation events, the memory allocation events, the kernel management, the Windows management of it all those things have to happen in a secure, trusted state before the program can even start. And then once it starts, all that is assumed to be trusted, and then you're good to go. But then then that process is open to attacks at that point in time. If you can slip inside the memory, if you can slip inside the process, if you can load another image, if you can load another DLL, if you can open up a file that it shouldn't be opening, if you can expand the memory more than it should, etc., it's going to fire. That's the problem. You can't do any of those attacks before that. So Karina, the stack is more vulnerable, but we're encouraged to use local variables. So that's just it. Is the more you're using local variables, a lot less of these attacks are going to happen. Finax, so the stack is just for storing variables. Where are these instructions that tell that is to be executed? Let me read it again. So the stack is just for storing variables. Where are these instructions that tell what is to be executed, stored? Well, that's the code. The code that you write, Finac. And then when it's compiled into a binary, those are binary instructions. Agent, what's going on? Spencer, the instructions are in the text portion memory? Maybe, yeah. I'm not 100% sure, actually. Be worth taking a look. Yeah. Because I think, like, I'm trying to think. I think you're right, because, like, the file structure, the .text, yeah, I think it is. I think you're right. That makes sense. So when we're talking about, like, the file structure, right, we have, like, our headers, we have, like, .text, data, resources. There's a couple different, like, containers inside of it. I think it's .text. Yeah, makes sense. Okay, Finna. Cool. Okay, good. That's where I'm going to stop, though, because this is where then you start specializing in like full courses, full modules, getting deeper into deeper. We're still like a SOC tier 1 level where we're just trying to triage someone clicked on a phishing email, like a malicious domain. So we don't want to go too crazy and too ahead of ourselves. But that's effectively the two memory structures that I think is important to understand at this stage in time, and sort of how they're working together. Now, let's talk a little bit about what this process actually looks like. Do we cover that in the CDA course by any chance? We do a little bit more, yeah. We do a little bit more on the memory forensic side. It does get a little bit deeper, somewhere between like a tier 1 to 2 level. And we are working on some deeper content right now. It's going to be coming out soon. That it's going to be more focused, sort of like a 3-day course you can do over the weekend live. That's where Johnny's coming in, that instructor in the team, the new one. He's going to be doing like more deep dives into like Windows internals and that type of stuff. So look out for that, Fnac. For those of you that are a little bit more advanced that want to kind of specialize in that area. Cool. Okay. So let's talk about what the process actually looks like. We saw the process view inside of ProcExp, right? PID, DLLs, threads, all this stuff, right? We saw all of that. Okay, so will that be a separate course, part of the ones that are specialized already? Separate course, man. Yeah. It's pretty advanced stuff. Yeah, it'll be a separate course. So what we're seeing here, DevOps morning, what we're seeing here is the process, right? Like this is what's inside of ProcExp. This is what's inside of Task Manager when we're looking at it. But do you all remember when we were back in SOC 100, like the beginning? Do you remember when I was saying how things are a representation of something or an abstraction of something? That everything is effectively like a series of ones and zeros, and files on the disk they don't look like a file on the disk, right? Like they're a representation of zeros and ones, etc. And then it's sort of interpreted for us to be able to work with. Yeah, okay, cool. You remember all that? So now, remember we talked about data structures? So that's the second question. We talked about data structures. We talked about that concept of like an object, right? Like, if I have a car. That's a terrible start to the car. Let's give it a square top. This is like the worst car I've ever seen. Okay, all right. So here is the car object. It has color, size, weight, speed, right? We talked about data structures. Doug's saying, yeah, it's weird how all this stuff loops back. Exactly, right? It's not like we just like slapped together a SOC 100 yeah, KS manual 100%. cars should only be manual. I don't know why people would ever drive automatic. That's my own hot take. But yes, so all that being said, okay, so we have this data structure, right? We have this thing that we can declare, and is that a Cybertruck? Yeah, pretty much, right? Okay, so this is a Cybertruck car, and it has properties. This is where we give this notion of working with objects, like object-oriented programming, where we declare a structure, sometimes referred to as like a struct, and this structure has properties like car.weight, car.size, car.speed, Cybertruck.cost, too much, right? All that stuff. So the process is also a data structure. Also, thanks to the follows. Jarvis and Smoothly, thanks for being here. Yes, like attributes. Okay. The process is also referenced from a data structure. And we actually get more into this in like CDA and stuff as well too. So again, we're just going to kind of highlight how this stuff works right now. The process itself, if I were to say that this is a process, okay, this is actually the reflection or the abstraction of something called the EProcess. Just when you thought you knew it all, right? Just like we have these threads are actually represented by EThreads. Now, what these stand for is executive process, executive thread. We talked before, like how the kernel is sort of like the engine, right? Inside of the car itself, where it's handling all the functions, and then you're the passenger in user land, doing your own thing with the wheel. But the wheel is turning something in the engine, and then the engine does it. And that reference, like the wheel itself, the steering wheel has an arm that connects to the engine. That space right there is the separation between you being in user land and the kernel, or sorry, the engine being in kernel land, or user space, kernel space. Again, up to you how you want to refer them to. Now, what's happening is the process is actually declared inside, and it is a kernel object called the executive process, or EProcess. Now, what we're seeing is the reflection of that inside of Windows itself, inside of like ProcExp and Task Manager. We refer to that as a process. Now, there's a lot more to that, of course, of things going on, but it's a data structure in and of itself where it has these certain properties. And, you know, it's important to understand this because when you're performing like, I don't know, malware analysis, right? You're actually trying to get as deep as you can, inspecting EProcess fields to see how certain attributes are changing that you can't see at a high level with something like Process Explorer and Task Manager and such. These tools like Process Explorer are just inspection. They're sort of like, okay, your car, you take out the little the oil stick, right? You take that out to see the oil level and how the quality is looking. You have readers on your dashboard that can let you know like your coolant, your temperature, your all those diagnostics and metrics of what the engine is doing, the performance of it. That's like looking at something inside a Process Explorer or Task Manager. It's still quite high level. When you start to get deeper in this field and you start getting to things like malware analysis, reverse engineering, you need to get inside the engine. And this is where like reverse engineering comes in, and this is where like deep levels of digital forensics comes in, where you need to actually get inside the engine and see what's happening as the car is running. You get inside, so not just under the hood and under the engine. That is what like true malware analysis and reverse engineering and digital forensics looks like. So for you, we are going to be focusing on this level right over here. This is what we want to inspect, but it's important to understand. So this is like SOC Tier 1 and SOC Tier 2, truthfully. Like, you're not really going deeper than that before and in those stages. It's important for you to understand that it's a reflection of it because, again, that's where you want to go. That's where you want to study. That's where you want to specialize. Does that make sense? I'll be more clear. So when you've got like Doug over here inside a chat and other advanced analysts and threat hunters, they're sort of like living in this space. They're trying to get deeper over here. That's where you want to go. But your tier 1 to 2 triage is effectively still living in this space before that. So it's important for you to be able to communicate that inside of interviews, that you can understand, right? Like it's a data structure, like an EProcess data structure working inside of kernel space as a kernel object. And our job at this level, at this tier, is to inspect the reflective activity of it for anomalous activity and anomalous changes in that runtime state. So I hope that gives you some guardrails too. Like when you're trying to look and try to study and get more advanced in this area, right? This is where you want to start looking into more of those common threats, common vulnerabilities, instead of being like, oh, I want to go and learn how to like, I want to go write my own 0 day. And you're like, you don't even know how to inspect the process yet, right? Like it's that can really throw you for a loop and put you in the wrong direction. Cool. Doug's in his own lane, yeah. Learning from everyone. We're all learning from everyone, man. I mean, like, there's obviously things that we know and we're confident on, for sure, right? But I don't know everything. No one knows everything in this field. This is like, we talked about that. It's a team sport. It's too big. It's too vast. So you need to rely on specialists. Okay, next order of business to talk about is the concept and definition of what these executables and DLLs are. This is a big one. I'm going to give it a special banner, because it's actually pretty important. But this is now where you're getting more involved. KS wants to be like Doug when he grows up. We all want to be like Doug when we grow up, man. I want to be like Doug when I grow up too. Doug's saying, yeah, Anthony, we should have an advanced class making a piece of malware and use it to hack the FBI. Yeah, we could do that. Actually, I shouldn't say that. I shouldn't be saying that I want to hack the FBI on stream. This is all in jest, whoever is watching this. Now, I can't be certain that someone in chat would or wouldn't. That's up to them. Don't do it, by the way. CI, are you asking me if I have a mentor, or are you asking if Doug has a mentor? Or rather, who are you asking that question to? Zeno is saying, will there be a class on how to find 0 days and writing exploits, then how to market and sell them to government to make millions? That's a stream on a different platform. That's where that class is. I always joke about this, like when we teach the CDA course, is just as there's a room inside here, like all of you learning how to be like the good guys, like the defenders, and there's instructors that are walking you through it. There's also like the bizarro version of all of you that are actually learning how to be criminals, and there's like an experienced criminal threat actor that is teaching them how to hack and do these things, but in the worst and the wrong and the bad ways. It's the same thing. It's happening right now. I can guarantee you this. Just as like all of you are learning how to defend, there is another bizarro version of us. Like there's evil Ariel, evil Doug, evil Zeno, evil KSJ, and evil CI. There's evil versions of all of you that are out there and being taught by the like evil Anthony and evil Doug. It's legit. So, you know what those evil versions of all of you are learning? They're learning how to what? They're learning how to attack the runtime state. That's what they're learning right now. And you are learning how to defend and identify anomalous activity in the runtime state. You see? You see how we're prepping you to defend against those threats? That's why we're teaching you this stuff. Wild piece if you want to hack the FBI Works contractor. Yeah, right? Demoriate. Oh, I didn't even think about that. Yeah, not level effect, but like, how would I even say that? Level effect? Yeah, yeah, that's like the evil version of level effect. That's pretty good. Okay. Maybe that was planned all along. Okay. the real APT has been here all along at level effect. Level effect. Okay. All right. So, let's talk about these two things because you're going to be working with them a lot at your level. Okay. Finax, you should put your offensive sec trading into legal effect. I mean, yeah. I mean, I am going to stream my my pen testing foundations and fundamentals later. I still have it. I made it. It's there. I just need to actually go and unearth it. So I'm going to stream that later. That's going to be fun. It's going to be like this, but for pen testing. Not that there's so little pen testing training out there, right? There's just, it's so hard to find. We'll see. Okay. So an executable file. There is a difference between the two of these things. And we talked before about the PE format. They share the same format. They're both a portable executable. That's right, Beard. Let's focus. Portable executable format. Okay. Now, sort of like the clear difference is to understand that the .exe. Let's kind of break this down. What this has over here is an entry point. Okay. We're gonna actually kind of look at the file structure in a moment. And the .dll is meant to load, okay? It is meant to load code into an existing process to share functions. Like, for example, think about maybe, I guess, like maybe a video game, right? Oh, sorry, yes, KS. I should actually define that, yes. A dynamic link library. Yes, yeah. So executables can run independently, and when they are executed, once they actually start, and you can't do this with the DLL. You can't start a process. It doesn't have the entry point. That's sort of like the main difference, is that the executable starts the process that we've already looked at. The PID, the threads that execute, the memory allocation, etc. And a DLL, a dynamic link library, is just a bundle of code that multiple binaries would share. So if I had a certain code that needed to use my GPU, like my graphics card, to render a window on the screen. So like this iPad window, right? You see how like I'm moving it around? Oh geez, I just realized I did not update the stream title, did I? 1 second. Now that I looked at it. 1 second. Okay, I'll get that in a moment. But as I move this iPad window around, right? Remember that my mouse, the click, the signals that are going is actually making API calls. It's like the steering wheel calling the kernel to do something and then make a change inside of my hardware, like my monitor, my screen, etc. That kind of comes back. Now, if I'm using my OBS, like Open Broadcaster software now, to have my stream preview that I can move things around, well, guess what? My browser, my Windows desktop, my GPU is being used by all of those. So there will be DLLs, there will be shared code that all of those processes can run and reference to and pull functions from. This is just software development best practice so that you don't have to write every single piece of software for every single piece of software. You don't have to reinvent the wheel. If you know you need to call your graphics card to render a window on the screen to do something, well then you're going to make every software that you ever make, and games and Adobe and all these things will use that same function, that same code. That is what the DLL is. So like my OBS broadcaster is a process running. My browser is a process running. My desktop is a process running. All these things are running, but they're pulling shared code from these DLLs, from these dynamic link libraries. Yeah, 53 people in the stream. Nice. Good stuff. And so KS, yeah, so it's like a referential bit of code ready to jump into a process effectively. Yeah, Tamori. DLLs allow code to be run by multiple applications at the same time, so those data can be used by malicious applications to perform systematic actions. Yeah, effectively. And this is why I was saying, like, this is where you get things like DLL injection. This is where you start getting these injection attacks that are happening. Because by design, Windows and other operating systems, they all kind of do this. They use shared code. They use shared libraries to make things more performant and more efficient. But that comes at the trade-off, because remember, security is always the balance between usability, that convenience factor, and security. You're always kind of like balancing that scale. So we want to make it convenient for everyone to be able to write code faster and develop software faster. And in order to do that, we have shared libraries of code that all this software can use. But again, that's a problem. So, for example, and we can actually kind of, we can sort of break this down and sort of what this sort of looks like. Let's do something like this. All right, and we'll actually update the stream while I'm at it. Okay, what are we doing? We're doing Windows Triage, DLLs, EXEs, threads, etc. Cool. Windows Triage. All right. So what do these files actually look like? Well, if we wanted to see, a file is kind of similar to encapsulation that we've seen inside of transmitting data over the wire. When we looked at a PCAP and we had those layers, right? The OSI model, we kind of broke them down all the way up to the application layer, and we saw that there is a header and then there's data. Header, data. Header, data. It's effectively what a file also looks like. So we learned before that these files are representations of zeros and ones. We kind of left it at that. But let's look at this a little bit more now and kind of see what one of these files would look like. We would have something over here like the DOS header. Okay. PE header. So this is where you would see things like MZ. And then we have like a general section table. And this is where we start to get into these individual things. So like where does the code actually live? Okay, so we get this thing like .text, .data. We also have our Beaver, yeah, portable executable. Yeah. So .text, data, BSS, resources, yeah, .bss. I think I'm gonna need a little bit more room. .rs, rc, .reloc. I think that's it, right? Is the box? Yes, correct. Yes, Karina. This is for a .exe that we're dealing with right now. So this is, you're right here somewhere, totally different, Beaver. So this is your code. Like this is where your code lives inside of this executable file. We also have our variables over here. Rather, I should say initialized. So like ones that we've declared. Uninitialized. Yeah, you can see that, right? Yeah, okay. And then we have a resources and a dynamic relocation. Now, again, this is more so to get a conceptual, general understanding of what this executable file looks like. The more you get into this, the deeper you get, the more you can specialize. You'll start to actually dissect this stuff quite a bit. So first of all, you're going to see that MZ header. This is why you always see this. Like if you're inside of a PCAP and we say, you know, search for like HTTP contains MZ or IP contains MZ or something along those lines, or we're looking for like the magic number we're saying like this file header. This is why, because it's actually the structure of the file. This is how you can observe an executable captured or executed either in memory or inside of a PCAP. And this is why when you compile your code, it actually will live inside of the .text portion of the executable itself. Every single thing, this is why I said it earlier on, is following this format of like header, data, header, data, header, data. It's very basic. Remember, computers aren't smart. They're just very, very fast. Karina, glad we're going over this? Yeah, definitely. It's important to just like generally understand. Jordan, you're late here today. Just finished Core 2 exam, passed. Nice. Congrats. Congrats. Now, why is the structure what it is, right? Oh, I know, yellow mug, yeah. Red for coffee, yellow for water, so I don't mix them up. Beaver, the .text container is effectively, that's like your compiled code. So they are written into the binary. They're written into the executable. This is where that code goes. So when you're writing code and you're writing your PowerShell scripts and all that's, well, I mean, not PowerShell, I should say, but your C devs out there, right? When you're actually like programming, when you're programming with a compiled language, this is where you're going to go and have your compiled executable code go and live inside of. Okay, saying this breakdown of structure is pretty helpful. Yeah. Good. I'm glad it's helping. It's yeah, let me zoom back up. It's good to just like visually understand what you're dealing with. Binary. So Beaver's saying, so the binary can be searched for the binary.data. Yeah. This is where you'll do like dumps. A little bit advanced, but yes. So you can actually dump that section, and this is where you get like debugging. Like a debugger, you know what will make more sense about this? Is a debugger. Cool. So yeah, a debugger would allow you to effectively step through this data. Beaver saying, or do I have to parse how long the .txt is file? I think they're asking you if strings it will. If you strings it, will .text or .data appear? I'm trying to grasp how do I know where these are? Like, are these for the program or the binary program? This is for the binary, Beaver. So when you compile your code into a .exe, an executable, certain pieces of your code will go to certain areas over here. And that section table above will say, like, what is the metadata? Like, where does it live? Which section contains what? Excuse me. And your compiled code is going to be living inside of the .text, and then you have variables, and you have uninitialized variables inside of your .data and .bss. Now, when you strings a binary, it's going to pull as much as it possibly can from the binary in clear, readable text. That's it. Now, it's not going to give you a true representation of what is inside of like .text or .data. That's where you get a debugger. That's where you use like a dump tool, like readelf or I don't know, like object dump, IDA, Ghidra. Like this is where you use these debuggers and these command line dump tools to actually dump all of it and read through it. So Tom, I'm saying, just to make sure I'm following, right now we're looking at .exe and DLL, where the exe is the entry point for the process, while DLL type of executable. That is function setter that multiple programs can use. The table we made, correct. Yeah, you're following, Tom. You're good. The table is a .exe. You're following. Cool. Yeah, good. Good to see. I like that. I like seeing when students are kind of like clicking it, because this is complex stuff. I'm quite certain you're not going to be seeing this type of discussion happening in a lot of other SOC Tier 1 type of training content. This is advanced. So for those of you that are just seeing this the first time, you're like, what? Yeah. But we're trying to give you a visual and general conceptual understanding of what this is under the hood for now. So you have a file structure. In this case, we're looking at a .exe, and it has headers. And this format is done for particular reasons, so that if we're executing this file, one, it's going to create a process. So it has a process entry point, fires it up. And remember when we looked at the process last week, the process itself has things like memory allocation. So as soon as you fire this .exe, the .text, .data, .bss, those sections are interpreted. And then at that point, the process starts to do its calls. How much memory do we need? Well, it knows how much memory we need because it interprets that .text, .data, .bss, resources, etc. And based on its interpretation of that and how the computer is programmed to understand what's inside of those sections, there's an agreement and understanding how much allocated memory do I assign based on a set of instructions that could occur, and that's your stack memory. And then it goes through this. And then you have your heap memory that's also assigned for anything global beyond that with inside of those instructions. And then if it needs to pull in DLLs as right away as well too, again, you're getting more memory being assigned to the process. You're given a PID, you're giving thread IDs, you're getting permissions, memory protection, and this is all because of this file format. This file format allows us to do this and allows us to execute it in the Windows environment to perform the process creation birth, I guess if you want to call it that, like the life cycle of the process being created. And then finally it hits a runtime state where we see it running and it's live. Decompiler show this format as well, correct? Yeah. Yeah. And honestly, even like when you're looking inside of Wireshark, so like if I go inside of like Wireshark PE file, NZ, I'm sure there's going to be a screenshot. Right? Because I don't have anything ready right now. But, okay, here. Perfect. This is actually perfect. 1 second. Open image, new tab. Okay. So, again, remember when we were inside of Wireshark? And we actually looked for MZ. We were looking for an executable inside of it. This is why you see this inside of a PCAP. Like when you're looking at the hex representation of it, you can see the DOS stub. You can see that where it says like this program cannot be run in DOS mode. Well, take a look. This is why you see this here inside, because you're looking at the executable. And this is easier to understand because you've worked with this before. You haven't actually worked with debuggers yet. You'll get there. But you can sort of imagine like Wireshark is allowing you to get like a light debugger view at the hex pane on the bottom right to see like what the file is being structured and represented as. Now you're not going to get all of it because it's not a true debugger, but you can get some of it. You can get the header information and maybe a little bit more. But you can see right away, this cannot be run in DOS mode. That's why Wireshark is interpreting what it is, because the executable file itself has this DOS header at the top that says MZ. That's why you see it. Saying, sorry, can you explain the relocation portion at the end? Yeah, so relocation, you can sort of think of it as it's sort of like adjusting the memory address. Like there are multiple memory addresses of what your code is doing from the stack to the heap. And the relocation is sort of just like a check and balance, and it's adjusting it as it goes and ensuring that it's actually running the way that it should. Let's think of it like that for now. Don't get too hung up, by the way, in trying to like master memorize this file structure at this time. Finax saying, so I had a question regarding heap memory. Since memory is dynamic and this process just grow larger, and yes, exactly. So what you've just described there, Finac, is a memory leak. So if you're dealing with like C or C++ code, for example, and you instantiate, or sorry, if you declare a new thread, like in your code, and you're saying, okay, like, just for intents purposes, new thread, read file, write to file, close file. But if you don't have like a terminate function, a line of code at the end of it, if you're not actually exiting or closing or terminating that thread, it will continue to persist. It will continue to grow. It'll get out of hands. It can corrupt, and you get things like memory leaks. Or if you have maybe some poorly written code that is trying to dynamically assign way too much memory than it actually needs, well, that's another problem too. Now, when you're and this is why people write in like C# and Java and these languages that have that thing called garbage collection. Garbage collection handles that for you, but you lose a lot of the ability of working under the hood. So this is why you see, like, if you're getting into malware analysis, if you're getting into malware creation, if you're getting into those deeper areas, you're going to want to start working with like C or C++, or some of the newer languages that abstract that for you. Nakis, thanks for the follow. That makes sense, Finac? Yeah. So one last thing we'll cover, and then we'll take a little bit of a break. Like I said, we got a lot to cover. So, like, what does this actually look like in action? There's two things that you're going to be encountering quite a bit when you're at this level, when you're first starting. You're going to see run DLL 32.exe. You're going to see that. And you're also going to see something called SVC host. Or service host. .exe. It's kind of bothering me. There we go. Something happened to the pen size. Okay. So, yeah, run DLL. Okay. All right. So you're going to see these two executables that do different things. Now, based on what you know now about a .exe and a .dll, if you see something like run_dll32.exe, what do you think that means? Just take a guess if you don't know. If you do know, pause. I want the people that don't know at the moment, just give it a shot. It's called run_dll32.exe. Yeah. Just think about it, because I want you to also to develop. I kind of throw these little pauses, right, at times, because I want you to think about things that you haven't seen before. Run a 32-bit file, DLL being injected into your running process. A library for executing programs still use 32-bit architecture. Run a library for configs OS. Cool, good, yeah. Those are all pretty fair explanations. So yes, run_dll32.exe is an executable that also allows you to just run functions inside of a DLL. Now, it doesn't actually even have to be running for a certain process. It just allows you. Imagine it to be like the key that unlocks the function inside of a DLL that you can call and do things with. That's all that it's actually doing. DevOps, yeah, it allows the program to run a specific function of a .dll. Correct. It's going to download Lotus 3. I mean, maybe, if that's inside of it. So, like, the format for this, let's take a look at this. You're going to see something like run DLL32.exe, and it can run 32 and 64-bit. It's a legacy name. You're going to see like 32 because it's just legacy. But run DLL32 can actually run 32 and 64-bit instructions. Where it's coming from is going to depend. You're going to see one in System32, and the other one, I think, in SysWow 64. So don't get fooled with that. Yeah, but good. Really good to see everyone kind of just like thinking about it, because when you're beyond this stage after SOC 100, you're just going to see new things. Like, it's just going to happen, and you're going to have to make sense of it and make some type of assessment. So the format is going to be like run DLL32.exe. I'm actually going to move that. .exe. And then you're going to have like file.dll. So like whatever that might be, like shell 32 or something, I don't know. And then you're going to have some type of function. And that's effectively it. So why is this important? Oh, CI, the question, yeah, sorry. What it means, I wanted you to just take a guess of what it was. Run DLL32 is a .exe. It's an executable using the PE format. It has all that structure that we saw previously. All what it does is that it's effectively a small program. Imagine that's all Run DLL32 actually is. It is a small program. And it loads functions inside of a DLL, those shared pieces of code. And it could be any function. It could be like close desktop, right? anything. It could be any function. And when you're a developer and you're writing code and you're writing DLLs, your DLL code will have like function name, do something. And then when you're running run DLL32.exe, you're just going to run DLL32.exe on the DLL file and specify that function name that the developer gave for the function inside of the DLL file. It's not like it's some random cryptic, super hard to figure out thing. It's just literally what the developers have called it. And they have declared that if a user runs run DLL32.exe on the DLL file, well, it has to specify the function name that developer gave it, and then it'll be able to execute it. And DevOps saying, but I think sometimes criminals can misuse it to execute malicious DLL files. Yeah, of course. So, living off the land binaries, lol bins and GTFO bins is something separate. That is using trusted, normal, well-intended functions inside of DLLs and executables in a way that they weren't designed to, that can bypass or break permissions or security controls. Common example, like inside of Linux, is if you have pseudo permissions on a binary that can drop to a shell inside of it, like Vim or something else, and you run it with those permissions, then you will drop to a root shell immediately. That's what like lol bins and GTFO bins. They're misusing the intended design and just using that to bypass permissions. Wild Piece, does it run an instance by DLL, or as many DLLs can run each run DLL? One per. Yeah, so run DLL32.exe is running a single function from that DLL, and then that's all what that instance of run DLL32 is trying to do. So you're going to see lots of run DLL32.exe calls as a result. Now, what's interesting is a run DLL32 call on a DLL and a function inside of it could spawn a process. So it's not necessarily just your job to be thinking about like, well, where are the .exes? Like, let me just go and inspect what .exes are doing, what they're capable of doing. If you're on an incident or an investigation and you have some recovered DLLs as part of an attack or part of malware, well, you need to inspect it thoroughly to see what the DLL could also be referencing. So that's important to understand as well too. Cool. Okay, last thing, we'll take a quick break. Now, SVC host is nothing like dealing with DLLs. Windows uses svc host.exe. It's called service host. And what they do is they actually bundle a lot of services inside of one process. And they do this because if the developer, like if Windows knows in advance that multiple services are using the same things, it's just more performant. So like imagine if we had like, I don't know, DNS client, DHCP client. Well, instead of running those as individual services, we can group them together inside of one SVC host. So what this does is it bundles services that are similar or use the same DLLs. So why is that a problem? If I have an SVC host, say this, IE DNS client, And we're going to take a look at this later. Finax says, like, when we're actually on the workstation, we're actually going to go in and see what that looks like. Finax saying, so too much functionality for a single EXE, hard to debug incidents. Yeah, exactly. So you're putting all your eggs in one basket. If you're running an SVC host, Kim saying, is because there are a lot of these processes. Hard to see if one is rogue. Exactly. This actually makes it really hard for you as the defender, because it's all going to look the same. Like, if I go and just do a snapshot for now, SVC host ProcExp. Let's see if someone's got like a screenshot for me. Yeah, okay, here we go. Because we're going to take a look at this soon inside the lab. So like, this is what you're going to see. So immediately you have very, very limited visibility. You don't know what the process actually is, because for your lens, for what you can see, all you see is svc host.exe. But inside of it is going to be the services themselves, which are running as different threads, different DLLs, and it gets really hard to track. And not only that, the larger problem is that this SVC host that's running could be running multiple services and multiple DLLs, and if that SVC host is compromised, well, guess what? All those other services are as well, and those DLLs, it's all fair game. Yeah. So Doug's saying that like a malicious DLL, run DL32, creating a backdoor script when another Microsoft application executes. Yeah, exactly. Because again, remember I said, these are trusted now in this state. Now, the beauty is like Process Explorer is once you open it up and you double click it and you look inside of the services tab inside, well, you can actually see. You can see what services are being called. Now, we're going to be looking a little bit later because it's almost like I'm painting like a little bit of doom and gloom. Like why, like it's so hard, and it's actually not. We're going to get to something really shortly to make that a little bit easier. The purpose of SVC host or service host DevOps is a performant way for Windows to bundle together similar services or similar processes that share the same DLLs in advance and bundle together inside of one core process for memory management, performance management as well. That's all. It's just a Windows thing to bundle them together. It allows your hardware to run Windows better because Windows has so many services and things running. That's all. Yeah, Doug, you meant explore.exe. yeah, it's all good, man. But yes. So, okay. So knowing all this, and then we'll take a break, for real. What do you think happens when any of these things are starting? Like process creation, load DLL, read file, run DLL32.exe call. What does that look like? Like what happens with all of those things? Karina's saying, so could Windows have made a better design choice rather than bundling service host? I think your answer is just use Linux. Look, they've got the reasons for it. I don't know if that's... I think from a design perspective, I think that actually makes a lot of sense. And there are a lot of security controls that protect it. Yeah, to use Arch. Tom, so could you rephrase and understand the question? Okay. If an svc host.exe process appears, and it loads a couple services and loads a couple DLLs. Or if run DLL32.exe is called on a DLL with a function. Or a .exe is executed and a process creation event occurs. I think I just gave it away. Zeno, process and thread creation. Yeah. Every single thing that happens along the way with anything that we've covered today is an event. And this is why, if you understand how these things fundamentally work, then all you need to do as a good security analyst and as a good security engineer is 1, triage and hunt for the events that reflect the activity of what these things are doing and line them up to malicious threat actor patterns, or perform immediate forensics as it happens, like you're triaging it. Or as an engineer, you build tools that are monitoring for these events. So I'll give you an example. If a threat actor wrote a binary, a .exe that looked trusted, it was signed, and it was like Doug's trusted binary.exe. Okay? And you ran it. And everything looked okay. And you looked inside a Process Explorer. And everything looked okay. It had a signed process. It's pulling in, it's creating threads, it's reading files, it's writing the things. If Doug's malicious binary used rundll32.exe to call Doug's evil attack.dll attack now function, you would see that as an event. So if you're monitoring processes for load image calls, which would load a DLL into the file, you would catch it. And you'll only understand and know to look for that if you understand how these things actually work. That's it. So let's kind of walk through that. You double click a .exe, process creation event, memory allocation, process ID, load DLLs, read files, create thread, thread does something. All of those events, any single one of them, if they are following a normal expected order, they should behave a certain way. And then you're fine. But if for some reason you see a DLL being called in a completely different location, you have a problem. It's those events. That's what we're looking for. And those are the events that create your SOC analyst tickets. Those are the events that your detection engineers are trying to monitor and write detection rules to associate strings of activity. And that's what threat hunting is. Threat hunting is just that. You're just using known threat actor patterns, which are events, right? We talked about last week, like memory allocation. If I see like malloc, so like memory allocation on a binary, I don't know. If I see like Notepad running as a process and all of a sudden there's an event of like memory allocate 100 megabytes for like no reason, not normal. SV host would be able to camouflage some of the underlying running processes. Exactly, yeah. Yes, exactly, Cass. Possibly hiding malicious activity. Yes. It's harder and harder to detect when you keep layering things in front of things. Wildpiece, is it possible to have hidden events? No. But it is possible to hide your tracks in different events that isn't immediately apparent until later. An example would be if I wanted to, I'll give you like a common one. DNS. It's part of like we've seen this, right? In networking, you're going to have that in every web request, and you're going to see like A records, SOA. You're going to see text. You're going to see these records that we looked at in the past. Now, the text record should be minimal. It should be at most maybe like one or a couple, depending on like a normal transaction, and it should have certain configurations inside there for like your I don't know, like your email security or like trusted domains, etc. Something like it should be small. But if we see like 100 text records appear after you make a request to like evildug.com, I'm just going to be using a lot of Doug references today, then that's not normal. So those events are all observable, but the fact that you had like 100 text records appear, and then if you look at them and you see there's actually like a transmission, like, hello, this is Doug, I got on your system, all your base are belong to us. Well, that's where you would see it. You'd see those messages inside of like text records, or you'd see them broken up into fragments. So what are you looking for there as a threat actor pattern if you're threat hunting? You're looking for like anomalous spikes in text records of a normal DNS transaction. So no, your events they're never hidden, but they are, I guess I should say, scrambled. That's all. Pretty cool. Okay. A little break, and then we're going to actually take a look at some of this stuff. Yeah, so we're going to hop in a lab of multi-threaded applications, and we're going to actually use Process Explorer to like observe like the stuff that we're talking about. See these threads in action, and then I think we all have time for ProcMon as well too, to kind of take a look at that. Cool, yeah. I think we can do both, kind of back to back. Now we're getting into security space. Yeah, I know, it's definitely a late break today. I wanted to keep some cadence because we had a lot to cover. And I actually have to hop out a little bit earlier today. So I wanted to kind of keep the cadence going and cover a lot of ground in one single go. But that is effectively it, okay? So up until now, and we've covered the registry already. We've already covered this. So what we're going to be doing now, we've got a baseline knowledge of generally the kernel space, the user space, the middle layer in between with Windows API calls that can happen to get the kernel to do things and reflect it back. We have a general understanding of a process creation happening with properties that are part of the process, like the PID, the memory allocation, threads, etc. And we know that a process is created by running an executable as a .exe, which has an entry point inside of the code to create a process. It's built inside. And when it's compiled into a binary and you double click it, it starts that process creation. And during the process creation in and of itself, there may be DLLs that are loaded, and those DLLs are shared pieces of code. And we know that in terms of the DLLs to be executed, the developer might rely on something like run DLL32 to unlock the function inside of a DLL that it needs if it's not natively built within inside of the program. We also know that these processes that are running, some of them get bundled into an SVC host process, service host.exe. And then ultimately, through all of this, we know that Windows has a registry, which is essentially a database of different registry key hives. And they have a key value structure to them. And all of these processes, all these files on disk will reference that general Windows database of different registry key values to support the process as well. Now, that is as much as you need to know to get going and develop your security analyst triage skill set now. Now we're going to learn how to use tools to start inspecting these things that we've all talked about for malicious activity. And we're going to be doing this by using Sysinternals tools like Process Explorer, Process Monitor, Auto Runs, TCP View. I think that's it for now. There are more, but that's enough to get you started. And then we're going to teach you how to use those tools to inspect different like anomalous patterns. And that's what we're going to learn in this module. We have a couple of challenges down here after we teach you how to do that stuff. And you're going to perform triage at that level. And then the most important thing to take away from this is that everything that I talked about up until now in that summary is that there is an event that occurs for all of that. Every single one of those things that I mentioned, whenever there is an interaction, when a process created or a thread created or an execution or an interaction with another piece of data or another piece of code, another service, another software, another port, network activity, every single one of those things is reflected into a Windows event. Now, some of those events get turned into logs, which we pipe into a SIEM and we perform log analysis. Some of them don't. But regardless, an event occurs. And we're going to look at that inside of, I think this lab? No? Here. Inside of this lab, the Windows registry, we're actually going to pull up Process Monitor. And Process Monitor is a Sysinternals tool that allows us to inspect all of those events that can happen on a Windows endpoint. Does that make sense? That's it. Like we've actually covered everything that we needed to cover. From SOC 100-1 to SOC 100-2, we have now covered the landscape and the general structure and surface of Windows and how Windows Internals works enough to a degree that we can start being performant with SOC Analyst tools to triage challenges. Does that make sense? Right? Like it's not that complicated, right? Like after you kind of just like summarize it, that's it. Now, from here on, it's just about getting sharper, better, more refined in those areas. But that's the extent of the surface. So like now, if you want to get a better understanding of thread operation calls, great. Then start doing that so you can be better with Process Monitor. Like that's it. If you want to start getting a better idea about like attacks happening in stack or heap, well, cool. Go and learn more about memory and memory forensics and memory incident response. But now you understand generally, like your foundation is it's there. Now it's just like now let's just build on it. It took us since October, but we're here. Exactly. So now it's all about the practice. Now it's practice, get better, sharper, learn more things, and that's it. So October to January 18th. Boom. We made it. So had a couple follows there as well too. Tony, Roner, Amine. Thanks for the follows. Let's take an actual break, and then we're gonna go. Like I said, I've got a bit of Chaos D2. Chaos D2. I feel like that should be a bigger dice, if that's where you're going with D2. At least a D6, D12, or D24. Okay. All right, let's take a break. And we're going to come back. 58 viewers. Good stuff. Hang on. We'll take a break for like 5-10 minutes, and we're going to come back. We're going to actually start looking at some of these tools. So KSES bad guys in general try to maintain persistence and access, but maybe will not activate payloads until ready to ransom delete. Yeah. APTs will either do quick destructive scorched earth against enemy nations or just do long engagements. All bad guys want to maintain access without detection, so doing living off the land, yeah. Yep. Absolutely. Cool. All right. Got some juice this time. Need some sugar. DevOps4577, I just want to take a moment to give kudos and show appreciation. Well, thanks, man. You purchased the course and have been going through the videos since you couldn't catch the live classes. You've been in security for years, and while you know the concepts, what you've learned in just 3 weeks is incredible. Damn, nice. You're in video 20 now, and it's your first live class. You plan to finish the self-paced course for Monday. You must say this is truly $1 million knowledge. That's awesome. Thanks, man. Appreciate that. That's huge. Love hearing feedback like that. I'm glad that you're finding it valuable. That's exactly what I want to hear. Fantastic. Yeah, these threat actors can persist for months, even years. Correct? Yeah. Yeah, they can. Chaos D2. That was your designated for your COD squad? Yeah, nice. Nice. Tony, welcome. Just found the channel after passing your Sec Plus. Nice. Good job. Congrats on passing. Now you're here to level up. All right, well, it's time to get your hands dirty. Getting some blue team work involved. Yeah, hop inside Discord. KS has got you over there. Thanks, KS. Cool. Yeah, Tony, we're going through SOC 100 course right now. We're going through SOC 100-2, and we just wrapped up getting all the foundations laid out over the past little while. So now we're going to actually go and do an inspection into a multi-threaded app. So let's go ahead and fire up our Windows workstation. Sam0, thanks for the follow. Actually, we had a couple, huh? We got Roboot. I thought it said reboot for a second. Lummeter Jack, thanks for the follows. Thanks for the support. Ariel, you're going to be there tonight? Yeah, looks like you're all planning another little Discord sesh. Cool. Cool. All right, let's let that fire up. Bearded, yeah. Don't be afraid or intimidated. Yeah. Hop in there. Get in the voice channels. Yeah, it's a public channel. Anyone's welcome. Ariel, you're going to pick up Neuromancer and Ghost of Fire. Nice. Yeah, once you and Beard start reading Neuromancer, you're going to understand more of what the Sprawl actually is. And you're all going to start finding out all the little Easter eggs I leave in places. Jake Armitage is everywhere. Mr. Zen. Mr. Friggin' Zen. Good to have you back. Darkhawk, thanks for the follow. All right. We can stop talking badly about PHP now. We have a PHP developer. Join the room. All right, let's fire it up. Let's go. Open up the Windows Workstation. And we're going to take a look at lab multi-threaded applications. AC51 DOS, thanks for the follow. Thanks for being here. Letting it do the update. Updates are cool. Okay, so we're going to go open up our Windows Foundations lab data. And we're going to go to Windows Triage and Malware Analysis. And we're going to hold Shift, right-click, open up PowerShell window inside here. Nice little shortcut. Now, first things first, what we're going to do, let's go and see what these threads look like inside. Let's actually examine what they're doing. So we got a multi-threaded app that we've created for you. Oh yeah, sorry, it's called Threaded App. Threaded App. Let's take a look at that. So notice when I run this application, this is just a little binary that Rob had created, and all what it does by default is it's going to execute one thread. Okay, so we can see that the app is running with one thread at this time. So excuse me, if I open up Process Explorer now. Let's fire it up, take a look inside, see what this thing actually looks like. Now, remember, this is going to be way further down the list. This is well beyond WinInit. And take a look. Remember all those SVC hosts? Real quick, if I go and find, I don't know. Let's take a look at this, this service host, right? If I double-click this, let me know if you can see that, if it's too small. But if I double-click this SVC host, well, right away you can see that it's actually running the process of RDP clip inside. If I double-click it and go inside the Services tab, well, this SVC host is actually dedicated to the Remote Desktop Services service. That is what this SVC host is doing. And we can see the DLL that it's calling. It's actually being loaded from Windows System 32 termserve.dll. So if we saw a compromised Windows workstation that no one looked like they were logged into, but we saw DLL activity from termserve.dll under an SVC host.exe, well, hot damn. Looks like we've got ourselves a compromised Windows workstation where there's a remote desktop service activity when no one is logged onto it. You see what I mean? Now that you know, you can start looking out for these things. So that's a quick example of like these SVC hosts that you're going to see running over here. Now, parent services.exe is the parent process that spawns all of these service host executables. So if you ever want to do inspection, you can go through each one. And now Process Explorer is going to allow us to go and do a quick inspection, little virus total checks, if they've been signed or not, if they have any memory protection as well too, and if they've been verified by Microsoft. Pretty cool, right? Makes so much more sense. So let's go and scroll all the way down. And we're going to be loading... Hold on a second, close that up. We're going to be looking under Explorer.exe. And why? Because Explorer.exe is the parent process of this desktop experience that I'm in right now. As I'm moving this around, this is all a child process of Windows Explorer, which is Explorer.exe. Now, if I saw PowerShell.exe running a threaded app under one of these service hosts, that'd be really weird. You see how you're starting to like notice a delineation of what to look for, what's normal, what's not normal? So let's take a look. This threaded app is running right now. Now, on the bottom pane inside of Process Explorer, we can see underneath it right away that there's actually a variety of thread activity that's happening. Some of these are waiting on user request, and some of them are inside of the queue. Now, we can also take a look at the DLLs. There are a lot. There are a lot of DLLs that are being loaded into memory so that this PowerShell this PowerShell process can run this binary. When threaded app.exe is running, we can see that it's pulling in DLLs from the .NET framework. So this is clearly built on the .NET framework. So this is a C# binary that utilizes this. We can see a whole bunch of runtime library supporting files. Now, take a look at this. Threaded app itself is also included inside here, just by default, because these are just all the things that are loaded. And we can actually see that it says 1 out of 7.3. This has actually failed the virus total check. Now, if we go to options at the top, and we go to virustotal.com, we can check virustotal.com whenever we're just loading new processes and we have Process Explorer running at the same time. We can also submit unknown executables. So pretty cool. Let's examine this a little bit more. Here's the threaded app.exe that's running. A couple things we want to take a look at. Here are the threads themselves. And notice that threads also have a thread ID. Just like how processes have a process ID or a PID, threads themselves also have an ID. So we have individual thread IDs. Okay. Here's the strings tab that I mentioned before. On the file structure itself, if we ran a strings, which is essentially shorthand, like you're going to hear people say strings the binary, and all what they're saying is pull out all the readable ASCII text that you can pull from the .exe file. So it's going to look through the DOS stub, it's going to look through the PE, the file header, it's going to look through the section header, it's going to look through the .text, data, etc. And all what it's trying to do is pull anything that's immediately readable. Now you're not going to get a lot of information, but you're going to get some. You're also going to get things like .NET Framework inside here that you can extract just for analysis, and so forth. Cool. And as mentioned before, we also have the security tab where we can see what this is pulling. So now let's go ahead and I'm going to just terminate this, hit enter, and notice how everything went red right away because the process is now terminating. It's over. Now what I'm going to do this time is I'm going to run this threaded app.exe, but I'm going to give it a parameter of 10. And what this is going to do is this is going to now spawn 10 threads. And this is just by design. When Rob built the binary for analysis, all what it's doing is just showing 10 different threads. And it's just, let's just let it run. See what happens. Really craving a juice today. I think my body was lacking vitamin C. Cool. So this is running. If PowerShell seems to like hang up, that can happen sometimes in a remote connection like this. Just hit enter. CI, type in ProcExp. So it ran 10 threads, thread 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, they're all working, and you can see that the threads are all behaving differently. They're all doing different things. They all have different timers. And that's just by default. Like, this is from code optimization, intention, how your hardware is performing. Like, if we had a thread that was always running at like 50 seconds compared to the rest, that helps us debug and diagnose if I know what's going on. Now, why are we doing this? Well, let's take a look. Okay. I'm going to run this again. Oh, good old PowerShell. Okay. I'm going to run this again. And when I do this time, I'm going to hop back inside of ProcExp real fast, like as fast as I can. I want to grab this over here. So I'm going to hit enter. And when I do, notice it starts. Now I'm going to right click it immediately and I'm going to suspend it. You see what happened when I suspended it right away? Everything stopped, including the threads. If I look under the threads tab, I can see all of them. They are now in a suspended state. Now if I right click this and I go to resume. Now everything's going to just go and continue the way that it should. That's normal. But this is an observation for us to be able to observe threads in action. Now, notice something. If I run it again, I'm gonna kill that with Control C, and I'm gonna fire it again. And as it's going, I'm actually gonna double click this, and I'm gonna go to the Threads tab. I'm gonna grab one of those threads IDs, and I'm gonna hit suspend. Okay. Maybe I'm gonna grab another one and hit suspend. So I've got 2 of those threads now suspended. Now take a look at this. Under the Threads tab on the bottom pane of threadedapp.exe, we can see over here that the rest of the process is actually going to continue. But take a look. So 1, 2, 3, 4, 5, 6, 7, 9. It looks like those actually all ran. And they executed and they finished. Mosh, thanks for the follow. But where's 8? Where is 8? Well, 8 is really afraid of 7. Do you know why that is? Do you know why thread 8 is really afraid of thread 7? Yeah, sorry, I just had to. Because 7, 8, 9. No, I had to just because, I mean, of all chances, I was able to grab thread 8 and suspend it. Now let's take a look. So we actually have 2 suspended threads, and the rest of the process has continued executing. So this is a demonstration of multi-threaded apps in action. You can see that each thread independently did their own thing. But thread 8 and whatever else I captured over here by going real quick, well, I suspended both of them. And the process still exists, but the rest of the process is just in a waiting state. It doesn't know what else to do anymore. So I don't know, let's go and resume this one. Let's see if that was 8. No? Okay, so that was probably like the core. That was probably the main thread that spawned all of the threads. Nope, that was 8. Okay, okay. So actually, that was actually thread 8. The other one was the core thread. But pay attention. Thread 8 ran for 19 seconds. Did it? Did it actually run for 19 seconds? That's the question. So what do you know now about the integrity of what I just did? If this was like a chain of custody. If you were doing a forensic investigation and you had event logs that showed the threaded app started at a certain time, and this was the recorded output of it, and it said thread 8 ran for 19 seconds. And that's what your event log said. So what could you do in this type of situation to get the full forensic capture of this to make sure, and just conceptually, it doesn't have to be specific like the actuals. What could you do? What could I be looking out for to determine how long this process actually executed for? Yeah, event logs. The event itself. Yes. What event? Conceptually here, tell me, what events would I be thinking about? Good. Yes. Good. Yeah. Start and end time. Good. Good thinking. Yes. PID time is good too. Good. I'm trying to get you to craft your analysis a little bit. And you want to be thinking in this like structured order of events. Start, end, create, terminate, read, write, execute, load, unload. Like think about things that could happen in the process creation and process execution and process termination. In security, we're interested in all of those things. And then what we want to do is match them up against the event logs. Because in this case, if the event log said that thread 8 ran for 19 seconds, but it clearly didn't, because there is an actual process event that happened of like process start and process end. So something's wrong, right? And then we could look for the thread ID itself. Pretty cool. Now let's take a look at ProcMon. So this is process monitor. Oh, I already actually have it there. So I actually had that there for, I think I was testing that the other day. Yeah, see, Doug, can't trust it. Also look at if there are any stops or gaps within the process. If the thread had a blip or three, exactly. Yeah. Now we're doing security. Like now we're doing actual analysis and thinking about this. So process monitor. Remember when I said every single event is captured? By default, when you open up process monitor, another Sysinternals tool, you get every single event that's happening on the Windows endpoint right now. Read files, TCP send, TCP receive, registry key queries, registry values, you name it. And it's going to keep on going. Like if you take a look in the bottom where my mouse is, it's now showing 160,000 events have happened. And this is backed by virtual memory. Yeah, DevOps. Compare timestamps from process creation, termination events, and logs. Yeah, event IDs would be really good, or event tracing. Yeah. Now, remember, those logs themselves, they're post-incident. They're post-action. So now let's look at process monitor. Process monitor is really, really cool. So I could go over here. I can hit filter at the top. Now take a look. The drop-down menu. I have an option here of many things I can look at. Process name is going to be a big one for you. DevOps saying also for deeper analysis, you can also check pin time, CPU usage. Yeah, you can actually get it like the hardware level. Yep. Excuse me. Need to drink more water today. So let's take a look. If I go process name, here is threaded app.exe. I'm going to add this and hit apply. Okay. Notice that there are no events. So if I'm doing some analysis, let's just say I did threaded app.10. Well, now I've got every single event that happened with this process. And I mean every single event. You want to do defer? You want to do analysis of what this binary did? Here you go. Every single thing. Thread create, thread exit, thread create. They're all here. Look in the beginning. This is the process creation lifecycle I was talking about. Here's the operation. Process start. Thread create. And sorry, actually, I have the highlighter on right now. So if I'm going to remove this. 1 second. Sorry. Inside of process monitor, you can actually use the highlight button here at the top. So if I hit highlight, I can now highlight things I'm looking for inside here. Let's just say like operation is... here's all your thread operations that could happen, like load image. So maybe I want to highlight all the DLL activity. Let's add this. Maybe I want to highlight let's see over here. Let's highlight thread create. And then let's also highlight thread exit. We're going to add those on. Okay, hit apply. So now we actually can highlight visually to see what's actually happening here. And if we wanted, we could actually just filter for those things and get rid of all the noise. But let's just do this like the whole way. So we can see here, thread created, loaded images. So it loaded the thread at app.exe. It loaded the Windows System.32 ntdll.dll. These registry keys were opened and the values were read. It then created a file. It actually created a file. And then it did some querying of another DLL. And then it loaded the DLL. So first it queried it, and then it loaded it. And then, take a look at this. There's kernel32.dll, not exe, but it's kernel32.dll, kernel base. So it's pulling kernel information now. A ton more registry key activity happens next. Additional DLL calls. Here's more threads being created. Now it's querying the registry for .net. I'm sorry, .net. .net related values. Closes them. More querying, more loading, and these are all the threads that are doing their things at this point. And this continues. This goes all the way. So I wasn't kidding. You actually have every single thing. And then finally at the end, you have this. So let's take a look. And we'll do, so process name is threaded-app.exe. And operation is thread. Whoops. Thread create. And operation is thread exit. Okay, hit apply. Let's get rid of our highlight, just because it's going to be too much. So hit reset. And actually, you know what? Let's actually highlight operation is thread exit. Yeah. Okay, cool. Now let's go and do that again. Threaded app.exe. Let's spawn 10 threads. Let's hop inside here. Let's grab a random thread that just started. Let's suspend. Let's suspend. Okay. Let's see if I captured which ones. Did I even capture them? Was it, maybe I wasn't fast enough? We'll find out. Okay. So 3, 6, 2, 4, 7, 8, and 5. So we're missing 1 and 9 and 10, right? If I can count. Nope. 9 and 10. Okay, so I think I caught 1. Did I capture thread 1? Yeah, I think I captured thread 1. Okay, cool. Close that. So it looks like one of those, because it's not firing anymore. So here we have a new set of events that occurred. We have timestamps as well, so we can figure out exactly when this happened. Now, which thread IDs do we have over here? I've got 1788 and 6560. Okay. I'm going to clear my highlight, and I want to go to operation is, or rather, thread ID is 1788. 1788. Add. Okay. Let's see if that was here. And thread ID 6560. Okay. It's actually pulling in other ones, eh? So here's thread 6560. And here you can see its stack operations. This is way more advanced, but you can actually see the order of operations of what it's trying to do. Okay. Now, this all happened from 520. Okay. Now let's go back inside here. And I'm going to open up threaded app.exe. Or rather, let's go inside here, and I'm just actually going to resume these. 1788. And resume. 6560 and 1368. Okay. So we can actually see a big difference, right? So like the thread exit occurred of multiple of them, and then we held on to it. And 528 is when we saw the actual termination of it. Karina's saying, so maybe covered it before, but could you define what an event is? Yeah, I think KS got you. Yeah, it's just, yeah, that's it. And this is how you can use Process Monitor. Like, you can do this for anything. If I wanted to, now we have a clear picture. Yeah, like, yes, this ran, but if this is what our event log said, and maybe the timestamps weren't granular enough, because it's going to be pretty hard for you to get a lot of detailed logs on every single thing. But this is why you have like an EDR tool that sits on the agent. And this is why you have like agent or endpoint or host-based scanning. Your antivirus and your EDR are looking at things like this. That's what they're doing. They're scanning this. So let's clear that. Get rid of that. We'll do it again, right? Every time, like if you run a binary like this, we can see exactly what's happening with it. Very cool. Now, let's reset our filter, go back, clear the log. And if we wanted to maybe see what chat's saying. Yeah, you used ProcMon a lot in your last job. The application could function incorrectly if it wasn't. Yeah. Yeah. Yeah, it's true. Maybe covered it before. Could you find? Yeah, we could talk about that. Tomorrow, I'm guessing. Yeah, I can bypass that. So ProcMon is showing everything that's happening on the computer. Yes, Karina. Yeah, it's literally showing every single event that's happening on the computer. Now, these aren't being stored anywhere. What ProcMon is doing is it's just tapping into the view. That's all. Who's here? Thanks for the follow. So, yeah, who's here? Go ahead. But very, very cool. So when you're doing like binary analysis, if you're given a compromised, like if you had a challenge and it was like, okay, you're gonna compromise your Windows workstation and see what happened, you would run the binary, have ProcMon running, have ProcExp running, and then you would do a full analysis on what the process is. You'd be looking at like the dependencies, so like what DLLs are being loaded, what the threads are doing, what like consumption of resources are happening, is it signed, is it verified in virus total, etc. And then you would also have Process Monitor running the entire time, and then you would just filter through it. or rather even highlight at first. Just highlight and be looking for things. So like operation contains, I don't know, DLL. See if that's got anything inside here. No, that was a terrible example. Anyways, who's here? So lately I started my programming journey and I have been learning C. And every time I make a project or do a new code, and every time I run it, my antivirus gets alerted, tells me this Excel. It tells me this Excel. What? So you've been learning. Every time you're making a new project or do new code, and every time you run it, your antivirus gets alerted. Okay, so your AV is telling you that your binaries that you've created are malicious, or what? Like, what's the actual error? Your antivirus tells you it's safe? Safer? I don't understand. Or is it saying that it's not safe? Yeah, like I'm understanding, like your AV is flagging it? Because I think, is that what you're asking? Because yeah, it's flagging it. Yeah, you have to add some exceptions. Yeah. So you're saying your antivirus tells you that it's safe? Like, did you write malicious code inside of it, or is your antivirus telling you that it's not safe and it's alerting you on that? I'm a little confused on that part. Because if it's your AV telling you that it's not safe, then that's normal. You just have to put the binary like in a trusted location or add an exception to Windows threatened virus protection. Put in like a trusted folder. You could also sign your binary if you're more confident programming. That's all. That's normal. Yeah, that's okay. I mean that's good then. I'm not sure what's the problem. Oh, you mean okay? So like it's actually, I see what you're saying. So your AV is actually just scanning, and then it's alerting you, telling you that it's safe. I mean, well, what AV do you have? That could just be a feature that you have turned on. That could be a feature functionality. Your AV, because your AV is scanning it every single time. Yeah, it's a setting. Yeah, I mean that's I guess that's a Norton thing. I don't use Norton, but that's just a setting. It's a preference. Check inside like your Norton preferences to see if you can disable that if it really bothers you. But what's happening is your AV is effectively like looking at this on my screen right now, and it's just like looking for file. So like here. Okay, I know I just saw it. Come on. Okay. Too many operations. Let's clear that. Here you go. So what's happening is your AV is looking for events like this, like create file, close file, TCP send, etc. It's just looking for that. Yeah. Yeah, that's all what's happening, Hoosier. It's that's a Norton preference. I thought you were asking like if Norton was flagging your binary for it being malicious. But cool. So does that make sense? for everyone. Process Monitor is a tool that you're going to use to inspect all of the reflected events that happen for like a given process, a given binary, and it's a tool for analysis and investigation and triage. Because what you'll do is you'll run a binary here, or you'll hop on like a Windows workstation, and you might have like ProcExp or something similar, and you're going to be having like a rogue process or something that was flagged or alerted on by a detection rule, and you're going to go inspect that process like we did. You're going to pull it up, you're going to identify what the threads are doing, the DLLs, the dependencies, and then what you would do is you'd go inside a filter, and you would just do like process name is threaded app.exe. So that whenever something is running, you would actually get the full activity of it. Finac, what are specific events that we would look and go for him that's suspicious? Are you ready for the big it depends? Whoops, kicked my camera. Yeah. Yeah, who's here? Just take a look at the Norton settings, but KS got your answer there too, Finac. It depends on what's normal. So like all your DLL files should be inside of System32, right? As an example. But if you ran a binary and it's pulling like mscore e.dll from like C users Finac, that's not normal. That's what I mean. You would be looking for things that are deviating from what you expect that binary to do. And it's always going to be a case-by-case basis. Now, I think tomorrow what we're going to do is we're actually going to... So we're going to start off... I think we're going to do a little bit more of the Windows registry and Windows security and such. And then we're actually going to do... Let's take a look. Yeah. So I think tomorrow what we'll do is we'll hop inside of Windows Security Lab, talk a little bit about like security countermeasures, and then we're actually going to do 3 triages together. We're going to triage a persistence mechanism, we're going to triage a anomalous process, and we're also going to triage network activity. So 3 different types of malware we're going to do tomorrow. And then you're going to have challenges after that. And then I think we'll start the email security module by the end of it. Do you provide cybersecurity for any companies currently? Level Effect, I mean, we used to do quite a bit of services on the side. We haven't for a while. We've just been focusing on training and such, but yeah. If it's something you're interested, just reach out to us. And I still do a little bit of my own consulting on the side. But cool. So a little bit of a shorter stream today. Like I said, everyone, I gotta hop off. It's a shorter stream for me today. It's not the full 4 hours. So I was kind of pushing through that first break over there. But I think we're in a good spot. At this point in time, even right now, like if any of you wanted to go off script and actually run like a binary through or something, you could on your Windows workstation. I mean, like if you wanted to. So here we go. I mean, yeah, I would say if any of you feel comfortable, go and give one of the malware challenges a shot right now. Otherwise, I'm going to walk through it tomorrow. But I think you could get through some of them on your own. I think I'll gonna pause there for the day. So we covered a lot, got pretty deep, and we've done a little bit of analysis of a process together. Mr. Meeseeks, you're welcome. Hoosier, so if you would have the chance to go back in time and redo your tech journey a different way, or maybe what you think you could have done better this way after spending so much time on it, what would it be? I absolutely would not have rushed. I definitely rushed when I first got started, and I got really into the hype of like grabbing my Net Plus, Sec Plus. I grabbed my CompTIA certifications and I started my technical IT work before I even used something like Process Explorer. Needless to say, I had a very, very big trial by fire, sink or swim first like 3 months when I actually started. And I wish I would have known. But I mean, at the same time, like this was back in 2015 when I first started studying. And resources and guides and steps and like targeted training, it didn't exist. That'd be my only advice. And that's why I even tell students now is like, really take your time. This is not a rush. This is not a race. Because you can see a lot of it's a lot of layered knowledge that requires you to kind of build upon yourself. That's my advice. But I'll stop there. But cool. We're going to stop a little bit shorter today, guys. Yeah, good stream today. KS, thanks for the feedback. Sometimes you think you're moving slow. We have a tendency to create a lot of artificial deadlines for ourselves. Yeah, we really do. And I think that's natural. But cool. That's it for today, everyone. Like I said, it was going to be a little bit of a tougher stream when we get into the Windows internals. Mooncure and Nastigator, thanks for the follows. Karina, thank you. Thanks. Yeah, I'm glad you guys are all here. I'm glad you're enjoying all this. You're going to catch up on some material today. Yeah, today was a bit of a harder session just because of, like, it gets a little bit deep when we start looking at all the process events and everything. But just like I said on the networking portion and also, like, the registry, this is about as hard as it's going to get in those core areas. Now, I don't need to go and walk you through, like, the process bucket again. Like, right? Like, now we can open up ProcMon and we can actually look at the process events together as we do more hands-on labs. So our double so do you, even though you know it's best slow down, build a strong foundation, is natural. Yeah, today is definitely a bit of a harder one. I would say the best thing you can do for today's stream is not to try and, like, wait for the recording. Hop in the labs today. Hang out in the Sprawl later today. I think everyone, there's quite a few that is going to hang inside the Discord Sprawl channel. Hop inside and just start doing the work. You don't need to keep reviewing the lectures. Go and actually try out the labs yourselves and work together. And then tomorrow I'm going to walk you through 3 malware analysis triages. So we're going to do that together. Sense, thanks for the follow as well. So like I said, we're going to be looking at a persistence type of malware, a process-related malware, and a network-related malware. Hoosier, the only regret you have is that these tech jobs aren't that lively. So I feel that. I'll comment on that in a moment, and I gotta get going. But at the same time, you do enjoy. Sometimes think that, what if your final moment of life, someone asks you what's our greatest accomplishment, would I say, oh, I fixed a bug. Yeah, I having one of those moments, eh? Yeah. Look, I came from... You may not guess it. Like I said before in other streams, I'm actually like a huge introvert. I've just gotten good at the like presentation, but I still have to go and like die a little after this. And oddly enough, like I worked in hospitality for a number of years. I actually really liked it because of the one-to-one human connection. And it was a huge adjustment for me when I left hospitality and my job was like, okay, like go sit by the computer and you're not going to talk to anyone for the rest of the day. That was a huge adjustment. Now, it doesn't have to be that way. So you can get more involved. And like hospitality sociopath. I mean, I think hospitality is like you get the opportunity to really get to know people and you're creating a memory for them. And I think that's really cool. It's not for everyone, but I think it's really cool. And it's a huge transition at that point. Like I said. But it doesn't have to be that way. Because what I also realized afterwards was I could help people. And that's why I started teaching. That's why I started training. Once I had several years experience and I felt confident in what I could do, I said, okay, well, I want to go help people. Same like I did in hospitality. And that's why I'm here today. That's why I'm teaching. That's why I'm training. So who's here? And thanks for all, and for everyone as well too. Yeah, if you are feeling like you're missing a bit of the human experience to your tech work, hop on a live stream and teach someone something. Make a YouTube video. Hop on our Discord and host a stream and teach someone something. Help other students inside of chat. Go to a meetup. Go do an OWASP chapter talk on something. Go to a CISP, like not CISP, but an ISACA chapter. There's so many ways you can still get the human experience inside a tech-based type of life. And if you want it, it's available. Yeah, it's like it's a bit of a thankless job, yeah, totally. But I don't look at it like I should be thanked. You know? And I think that made it easier for me. Yeah, R-double. Yeah, back in 2015, I had no idea what Linux was. I knew of it. I had never even used it at that point in my life. I just knew of it. It just takes time. Who's your daddy? Yeah, your name? Well, apparently Dad's in chat, so who's your daddy? I think we found Dad. Yeah. Cool. We can save the... we'll have some streams in the future to talk about like the human-centric side of things. Who's here if you want to flex? No, man. You want to use Arch. Yeah. Cool. So yes, thank you all for being here. I appreciate the support. I appreciate y'all being on stream and engaging in chat, asking good questions, and showing up day by day. We're getting closer and closer to being able to do this. Each step. So we'll see you back tomorrow morning. And we're going to dive into the rest of the Windows Triage. Hack Smarter was about to raid you, but you're running a stream? Oh, man. No. Well, I mean, I'm going to be on tomorrow. If you want to come out, hang out tomorrow. That would have been fun. Thanks, Dad. Yeah. Well, Dad, tomorrow we're going to be doing we're actually going to start the triage analysis of malware. So we've been covering a lot of it, like the adjacent reflective activity of it, kind of getting the foundation down. But tomorrow we're going to be looking at persistence, process, and networking related malware and triage it. Doug, I'm not a superhuman, man. But Bearded, we're all AI. Every single one of us. We're about to find that out. Yeah, Dad, my background's in consulting and pen testing and the red teaming side myself. I started on the defensive arts. We'll be on tomorrow at 10 a.m. Eastern. But cool. All right. We'll call it for the day over there. We can chat tomorrow and have a good time. Tomorrow's gonna be good. We're gonna have some really good triage. Finally, looking at some malware. I only had you wait, what, 3 months? October, November, December, almost 4 months, and now I'm gonna say, okay, now it's time to look at malware. A lot of wax on, wax off. Dad, 4 p.m. Central? No, I think, what is 10 a.m. Eastern is what? 9 a.m. Central? Yeah, 9 to 1 Central. Oh, that's a European time? Sorry, I thought that was Central time. Tomorrow it is, you need a level 5 keep your job? Yeah, all good, Dad. I just think it's hilarious that who's your daddy is here and Dad is also here in chat at the same time. That's amazing. Okay, guys. Have a good rest of your Saturday. We'll see you back tomorrow. Thanks for being here today. Thanks for the engagement, the support, and we'll see you tomorrow. Have a good one.